So the discussion we've had so far has been about the Gaussian distribution and how we can use the Gaussian distribution to quantify the probability of something occurring underneath a curve, which will eventually lead to us having an uncertainty bound that we can give a customer or a user of our data. And so the example that we have here, again, very simple, but it should get you a little more comfortable with how to use the Z table. And the reason we're using the Z table, if you remember, we have the Gaussian distribution that we think our data samples are going to be represented by. If we take enough data samples, that the Gaussian distribution would characterize this, would be so similar to the data set that we're looking at that we can use it to characterize the uncertainty that we have or how good the measurement is. And so again, we have this equation here, 3.6. We could integrate this and figure out what the area under the curve is. And that area under the curve is the probability of something occurring. But instead of integrating it, we do have a table. And so this example is to help us get comfortable with using that table and looking up a value. So the question is, what is the area under the curve between the value for z of negative 1.43 and z equals 1.43? So that z is the number of standard deviations away from the mean. And so if you remember, we had 1.96, we had one standard deviation, we had three standard deviations, and those were equivalent to specific probabilities of having something occur within that range or within the area under the curve. And so this z value allows us to shift that range up and down based on how many standard deviations we want. And so you can see this is very handy for us to be able to define those uncertainty bounds. So let's dive into this, and maybe I can help bring some clarity to it. So once we find that area under the curve, what is the significance of the area? So in order to do this, again, we could integrate this, but instead we're going to use this table. This table 3.2 is going to become your friend. We're going to use it very often. So the area under the curve between these two values, what we do with this table is we look at the z value, which is the number of standard deviations away from the mean. So we go down here to 1.4, and then this next value, the 3, we use this top area over here. So we go 1.43. So you can see it is 0.4236. So that value right there is the probability of something occurring, or the area under the curve, for half of the probability distribution function, which is a Gaussian distribution in this case. So I point that out because this is a major tripping point for a lot of people who are starting to understand or starting to use the z-table. The z-table shows only half of it. We are interested typically in what's happening under the total curve from a positive to a negative. And in this specific case, we're definitely looking at negative 1.43 up to positive 1.43. So we're going to have to take this number and multiply it by 2. Okay, so we've got 4.4236. We need to multiply that by 2. Now, what is the significance of the area under the curve? Well, that is the probability of something occurring within this range. So you can see we are a little bit under this range right here where we are defining the uncertainty bounds. So we're saying the probability of something occurring within this range is 0.4236 times 2, or 84.72%. So here's the solution to the problem. From the table, we read this. Therefore, the total area is 0.8472. The significance of that data following the normal distribution is 84.72% of the population lies within that range. So again, if we had a bag of marbles, we reached into the bag of marbles, we pull it out, and we say we want 84.72% of the population to fall within this range, then that would be the area under the curve. So zooming back out again, we are talking about the total uncertainty is going to have a bias and a precision component to them. The bias and the precision components would then be square root sum squares pulled together. and that would be the total uncertainty. So we're talking about precision uncertainty only, which we can use statistical analysis. And we like the bell curve or the normal distribution a lot because it is easily characterized and it's well understood. And so if our data can be represented by a Gaussian distribution, we can now define what these uncertainty bounds are and say our population, our data set that we've collected that has this scatter is going to fit within these uncertainty bounds at a certain confidence, or the probability of something occurring is going to be a certain percentage. That is very valuable to us. So, what does the probability have to do with uncertainty? Well, if we can define what the probability is, we can now calculate that uncertainty bound. And so if we can say that our probability of something occurring follows the same rules or has the same shape to it as a Gaussian distribution, we can now very easily define what those uncertainty bounds are. So there is definitely a connection between the two that allows us to use statistics to quantify at least the precision part of the uncertainty.